Alright, today we are going to take a look at the Pythagorean theorem. Okay, I think this is something you've seen before, probably in 8th grade. The Pythagorean theorem is just an equation that relates the three sides of a right triangle. Okay, so that's a big, important thing. Okay, this only applies to right triangles. In this formula, A and B are the two legs of the right triangle. Okay? A and B are the two legs. So let's make a note of that. A and B are the legs, and then C is the hypotenuse. All right, A and B are the legs. Now, what do we mean by legs? What does that even mean? I mean, yeah, like not the hypotenuse, right? The other two sides. So the
the legs are what add up to or have to be bigger than the
So the hypotenuse is always the longest side.
Yeah, but don't the two legs have to be added together bigger than the
That would be true. That would be true of any triangle. The two smaller have to add up to be bigger than the third side. So one way of just kind of explaining what the legs are, right? We can just say the legs are the two sides that make the right angle. Alright, so in this first example, the two legs or the two sides that make the right angle would be BC and AC. Those are the legs, okay, the sides that make up the right angle. So in the Pythagorean theorem, those two sides are always A and B. It does not matter which one's A or which one's B, okay, just as long as the legs are A and B, and then the hypotenuse, which is the side opposite the right angle, is always C. Okay, so we can use this equation to solve for missing sides in right triangles. If I know two sides, I can always find the third side. So in this example, if I want to find this leg, I could set this up as, I'll just leave this as a squared because that's what I'm solving for. And then this leg is 12. So I want to take 12 squared and then equals the hypotenuse of 13 squared. So then, to solve for A, I want to first square both of these numbers. So what's 12 squared? 144. And 13 squared? 69. So now, again, to get A squared by itself, I would subtract 144 over here. So we'll get A squared equals 25. And then I still have one more step. How would I get A by itself? How would I undo this square? Square root. And so take the square root of both sides. And what is the square root of 25? 5. Now, technically, okay, I think you may have worked with this a little bit in Algebra 1 last year. Whenever we take the square root, we would technically have plus or minus, right? But if we're talking about lengths, we're only going to take the positive root, okay? So we're not going to include the plus or minus. It'll just be a positive length, okay? Questions so far? So this missing side would just have a length of 5. Let's do another example here, okay? So on this one, I'm trying to find the hypotenuse. So 20 and 30 are my two legs. So I would set this one up as 20 squared plus 30 squared equals C squared. Square both of these. So 20 squared is 400. 30 squared is 900. Now in this case, these are already on the same side, so I can just add these together. I would get 1300. And then, again, just like the last problem, I would take the square root of both sides to get c by itself. Now 1300 isn't a perfect square, so we would need to put this into the calculator and get a decimal. So what is the square root of 1300? 36.0555. So let's, they don't specifically tell us what to round to. So if they don't give us directions, let's go to 2 decimal places. So if it was 36 point, you said 055? Yeah. So how would I round this to 2 decimal places? Yeah, 0.06, okay? Since this number is 5 or greater, I would round the 100th place up to a 6. So 36.06 would be the length of my hypotenuse for this right triangle, okay? Now, one thing that we can always do to at least double check and make sure that our answer makes sense, the hypotenuse always has to be the longest side, right? So the hypotenuse has to be longer than either of these. If we somehow get a hypotenuse that is shorter than one of these, we know we did something wrong. Or vice versa. If we get a leg that ends up being longer than the hypotenuse, we know we did something wrong somewhere. Okay, so that's just a quick, basic way to double check and make sure your answer at least makes sense. Okay? Questions? All right, then let's try a few of these. Okay, so down below, we've got some right triangles. Okay, 1, 2, and 3 are all pretty similar to the example that we just did. But then 4, 5, and 6 kind of get a little bit different, but still not, because we're still looking at right triangles. And we're still trying to find missing lengths. Okay, so let's take a little chunk of time here and try all 6 of these, 1 through 6 here. So on all of these, we're going to use the Pythagorean theorem to find the missing piece. I'm putting up the answers. All right, take a look up here at our answers. Which ones do we want to take a closer look at? 4. Number 4? Yes. So on this one, first, if I label my sides A, B, and C, my 2 legs would be up here. So I can say these are my A and B, and then this is my C. So if I'm setting this up as A squared plus B squared equals C squared, I would have X squared plus 4/9 squared equals 5/9 squared. Now, if we wanted to square these fractions by hand, okay, all we're doing is squaring the number in the top and squaring the number in the bottom. So 4 squared would be 16, 9 squared is 81. Okay, that's how you square a fraction by hand. You just square the numerator and then square the denominator. But your calculator can do that for you as well. Okay, if you type in, or if you use alpha y equals, that will get you a fraction on the calculator. Okay, so if I do the same thing here, I would have 5 squared is 25 over 9 squared is 81. So then to get x squared by itself, subtract 16 over 81 from both sides. And we'll end up with x squared equals, I already have common denominators. So again, if we're thinking about doing this by hand, I would just subtract 25 minus 16 and get 9 over 81. And then we can take the square root of both sides. So the square root of 9 over 81, we put that in the calculator, we should get 1/3. Okay, or remember, if your calculator gives you a decimal, it would be 0.333333333, which is 1/3. Okay, so it's the same process, just have some fractions in there. Other ones that we want to take a look at, right? Number 1. So on number 1 here, again, thinking about labeling the sides first. two legs would be the 3 and the 3. So this would be A and B, and then X would be C. So my setup would be 3 squared plus 3 squared equals C squared or X squared. So then square my numerical values. So 3 squared is 9. So 9 plus 9 equals X squared. So add those together, get 18. And take the square root of both sides. And the square root of 18 is like 4.24. And it didn't specify what to round to in this problem. So if you had like 4.24 or 4.2, those would both be all right. Other questions on these? 7. So, yeah, we're going to talk about 7, 8, and 9 now. Right. No other questions on 1 through 6? 3? So on this one,
I got 8.
you got 8 and 9? So on 3, these two sides here, the 25 and the X, would be my A and B, and then 65 would be my hypotenuse of C. And again, remember, it doesn't matter which one's A and which one's B, just as long as the two legs are A and B. So my setup would be 25 squared plus X squared equals 65 squared. So we get markers about the 625 plus X squared equals the 65 squared is at 4,225. Subtract 625 from both sides. We get X squared equals 3,600. Take the square root, and that is a perfect square. We'll get exactly 60. Right. Other questions? All right, so let's talk about 7, 8, and 9 then. Okay. On these, the directions say use a Pythagorean triple to find x. Okay. Now, for all of these, we could just use the Pythagorean theorem just like we just did, okay, and get an answer. But there might be a shortcut. Okay. A Pythagorean triple. Go back up to the top here. All right, so it up here just kind of mentions a Pythagorean triple. What that is 3 whole numbers that satisfy the Pythagorean theorem. So this first example that we did was an example of a Pythagorean triple because our answer for A was 5. So 5, 12, 13 is an example of a Pythagorean triple. It's 3 sides of a right triangle that are all whole numbers. There are actually an infinite number of Pythagorean triples, okay? 3 whole numbers that satisfy the Pythagorean theorem. We're just going to look at a couple of them, right? So 3, 4, 5 might be the most common one, right? This set of numbers satisfies the Pythagorean theorem. 3 squared plus 4 squared equals 5 squared. Right? That would be 9 plus 16 equals 25. So 3, 4, 5 is one possibility for a right triangle. Another one we just said, 5, 12, 13, is an example of a Pythagorean triple. Another one is 8, 15, 17, okay, where our 2 legs could be 8 and 15, and the hypotenuse 17. And then the last one that we'll look at, 7, 24, 25. Okay? So these are 4 examples of sets of numbers, sets of whole numbers that satisfy the Pythagorean theorem. Right? So these might allow us a shortcut. Right? Now, like I said, on 7, 8, and 9, we could always just use the Pythagorean theorem. Okay? If we don't want to try to deal with Pythagorean triples, or try to memorize those, we can always just use the Pythagorean theorem. Okay? So I could just set this up. These are my 2 legs, so I could say x squared plus 8 squared equals 17 squared, and solve it just like we have been doing. Okay?
So the x is 15.
So, but exactly. If we remember this list of triples, I don't have to do any work, right? This triangle fits this pattern, right? So the two legs would be 8 and 15, and the hypotenuse is 17. So if we recognize that it's a Pythagorean triple, I don't have to do anything, right? We just use that knowledge and say, well, if one of the legs is 8 and the hypotenuse is 17, the other leg has to be 15. Bless you. Right? But again, if you don't remember that or don't recognize that, you can always use Pythagorean theorem. Okay? Now, with that, I can actually multiply each of these by a constant to get a bunch more Pythagorean triples. For example, if I multiplied 3, 4, 5, if I multiplied every single one of those by 2, I would get 6, 8, 10. Okay, that would be another example of a Pythagorean triple. Or I could take each of these and multiply them by 3. And I could have 9, 12, 15. Okay? That would be another Pythagorean triple. As long as I take each of these numbers and multiply them by the same thing, I would get another Pythagorean triple. So that's what's happening in this next example. Okay? We kind of want to look at these numbers and think, well, can I divide these by something? Is this a multiple of one of my Pythagorean triples? Okay, would I be able to divide both 45 and 24 by the same value to where it looks like one of my Pythagorean triples? What do you think? Does anybody see anything that I could divide these by?
7 or 25?
Well, so since that's a 24, it kind of looks like it might fit that pattern, but the other leg is 45, not 7. So what we can think about here, okay, if we think about common factors, each of these numbers are divisible by 3. So if I take 45 and divide that by 3, that would be 15. If I take 24 and divide it by 3, that would be 8.
17.
So then my hypotenuse here would be 17 times 3. Okay? Since this fits the 8, 15, 17 pattern, those numbers are just multiplied by 3. So my hypotenuse here would just be 17 times 3, or 51. Okay? But again, if you don't recognize that, you can just use the Pythagorean theorem. Right? So instead of using a Pythagorean triple, we could have set this up as 45 squared plus 24 squared equals x squared. Okay? Same for the last one here. Okay, in this last example, 28 and 96. Again, it might be difficult to recognize at first, okay? But if I take each of these numbers and divide them by 4, okay, if I divide these by 4, this would be 7, and if I divide this by 4, that would be 24. So that would fit my 7, 24, 25 pattern. So that means my hypotenuse would be 25 times 4, or 100. Okay? But again, yes, I'm not done.
Why did you pick the big line before?
So that I could see which pattern of my Pythagorean triples it fit. So both of these numbers are divisible by 4. So if I divide them by 4, I would get 7 here and 24 here. So then I can see that this is just a multiple of my 7, 24, 25 pattern.
So why'd you put the 100 up there then?
So then, my hypotenuse, if I think about 100 divided by 4, would be 25.
Oh,
So I just kind of went backwards and said, well, if it fits this pattern, then I would just take 25 times 4 to get that that side is 100.
okay.
Okay? So again, we don't have to use this idea of Pythagorean triples. You can